Okay. Same. In the last class, I have studied a little bit about solubility. Solubility means the maximum amount of solute that can dissolve in a given amount of solvent at constant temperature or fixed temperature is known as solubility. This solubility depends upon nature of solute, nature of solvent, temperature and pressure. Nature of solute, nature of solvent, temperature and pressure play significant role in the solubility of solute in given solvent. Same, generally polar solutes dissolve in polar solvent. There are many factors regarding solubility. Polar solutes dissolve in polar solvents. Non-polar solutes dissolve in non-polar solvents. It is generally considered as like dissolve like. Next one is the solute or the substance which can form hydrogen bonds with solvent. That solute can dissolve in that solvent. The solute or substance which can form hydrogen bonds with solvent, say water, then that solute can easily dissolve in water or that solvent. That is another point. Next one is the solvent to dissolve solute, particularly ionic solute, polar solutes, it must have high dielectric constant. Dielectric constant also plays a role on the solubility. Another point is temperature. Actually, that substance while dissolving, the substance or solute while dissolving, heat is liberated. That is, dissolution process is exothermic. In such case, rise in temperature is not favorable condition. Rise in temperature decreases the solubility. You know, according to Le Chatelier's principle, for all exothermic processes, rise in temperature is not favorable condition. Similarly, if solute while dissolving, heat is absorbed, that is, process is endothermic. In such case, rise in temperature is a favorable condition. That is one. Generally, the solute in which interparticle interactive force is same as that in the case of solvent, then that solute dissolve in that solvent. If to dissolve a solute in a given solvent, the interactive force or action between the particles in both the cases, solute and solvent, same, then dissolution occurs. That is another important point about solubility. In some cases, pressure also plays a role on solubility. Now, we shall see the solubility of gaseous substances, gaseous solute in liquid solvent. Let us consider solution of gas in liquid. Solution of gas in liquid, gas is solute, liquid is solvent, and totally the solution is in the liquid form or state. Example for such type of system: carbon dioxide, dissolved carbon dioxide in water. That is, when carbon dioxide is passed through water, some amount of carbon dioxide dissolves in water to form carbonated water, often known as soda water, carbonic acid. Dissolved oxygen in water, dissolved nitrogen in water, dissolved HCl in water, hydrogen chloride gas in water, so on and so forth. Now, let us see the factors which influence on the solubility of gas in liquid. It is observed that gases dissolve in liquid to different extent under different conditions of temperature and pressure, and solubility of gas in liquid varies from gas to gas, and it depends upon temperature, pressure, so on and so forth. See, here also the solubility of gas in liquid depends upon nature of solute, that is nature of gas, nature of solvent, that is liquid solvent, temperature and pressure. All these four factors influence on the solubility of gas in liquid. See, the gases which can interact with solvent, that means liquid, gases which can interact with liquid, such gases dissolve in that liquid solvent to a great extent. Substances or gases which interact with liquid solvent, then such gases dissolve in that solvent to a great extent, maximum extent at the given temperature. Example, HCl gas, sulfur dioxide gas, even carbon dioxide, sulfur trioxide, etc. They interact with water when passed to form corresponding compounds, acids, of course. When carbon dioxide is passed through water, you will get H2CO3, carbonic acid, sulfur trioxide, sulfuric acid, sulfur dioxide, sulfurous acid, HCl, hydrochloric acid, so on and so forth. So, the gases which can interact with the solvent, such gases dissolve to a great extent in that solvent. On the other hand, the gases which do not interact with solvent or interaction is very, very small, then such gases dissolve in that solvent only to a little extent. Small amount of such gases dissolve in that given solvent. For example, if you pass oxygen through water, okay, certain amount of oxygen, only little amount of oxygen dissolve in water, because oxygen does not interact with water fairly or greatly. Similarly, nitrogen, helium, oxygen, they do not interact with water to a great extent. Therefore, their solubility in water is very, very little, small amount. Next bit is temperature effect. This is about nature of solute and solvent. Next one, let us see the effect of temperature on the solubility of gas in liquid. In fact, on rising the temperature, solubility of gas in liquid decreases. This is due to the two facts. One is, when gas is passed into the liquid or when gas is dissolving in liquid, the gas molecules undergo condensation. This condensation process is exothermic in nature. Heat is liberated. So dissolution of gas in liquid is an exothermic process. So high temperature is not favorable as per your Le Chatelier's principle. So on rising the temperature, solubility of gas in liquid decreases because the process of solubility of gas in liquid is exothermic in nature. This is one point, one reason. There is another reason about the decrease of solubility of gas in liquid. See, when gas dissolved in liquid, when you rise the temperature, the dissolved gas molecules gain the kinetic energy. You know that kinetic energy is directly proportional to temperature, one of the important assumptions of kinetic theory of gases. So, on rising the temperature of the system, kinetic energy of dissolved gas molecules increases. As the result, their escaping tendency from the solution increases and simply escape from the solution. As the result, concentration or amount of gas in the solution decreases. So these two factors are responsible for decrease of solubility of gas in liquid on rising the temperature. Next, we shall see another factor which influence on the solubility of gas in liquid, that is pressure. Generally, on rising the pressure, solubility increases. On rising the pressure, solubility of gas in liquid increases because the gas molecules can undergo association or condensation in the liquid phase. So, rising pressure increases the solubility of gas in liquid. Henry, a scientist by name, Henry had studied the solubility of gases in liquids under various pressures, and he framed a simple relationship between pressure and solubility of gas. He framed a simple law known as Henry's law of gas solubility. This Henry's law of gas solubility states the partial pressure of dissolved gas, in its vapor phase, that is above the surface of solution, is directly proportional to the amount of gas dissolved in the solution, that is mole fraction of the dissolved gas, a chi. This is Henry's law. Of course, when temperature remains constant, the partial pressure of dissolved gas in its vapor phase, that is above the surface of solution, is directly proportional to its mole fraction in the solution at constant temperature, that is when temperature is constant. This is Henry's law. We can write this Henry's law or mathematical form of Henry's law as P is equal to KH into chi. Here P stands for partial pressure of gas. Chi stands for its solubility. Solubility is generally expressed in terms of concentration in the solution, that is in mole fraction. KH, it is a constant. It is known as Henry's constant or Henry's constant of gas solubility. We just call this equation as 1. Okay. Now we can write this expression as P is equal to KH into chi plus 0. We can write, no change in it. See, 0, it is a constant term. Let this constant term be C. Here pressure and mole fraction, that is concentration, are variable terms. They are variable terms. Let this variable term P be Y, chi be X. It is constant. Henry's constant is constant for a gas at a particular temperature. Henry's constant for a gas depends upon temperature. For a gas, Henry's constant varies from temperature to temperature. And Henry's constant varies from gas to gas also. Okay. Now, P is equal to KH into chi. KH is Henry's constant. Let this constant be M. Now, it is Y is equal to mx plus C. We know that Y is equal to mx plus C is an equation for straight line. This shows your Henry's equation is also in the form of straight line equation. Henry's equation is in the form of straight line equation. So, the plot of y is P against x. X is nothing but chi. What is chi? Mole fraction of gas, dissolved gas in the solution. Must be a straight line. Okay. Now let us see the characteristics of this plot. See here, the value of this C, that is constant, corresponds to 0. Shows 0. Generally, from the plot, this value C can be obtained by considering the intercept of the plot on either x-axis or y-axis. Here, the value of C is found to be 0. This indicates straight line passes through the origin. That means, in the plot there is no intercept. It means the plot of P against chi, partial pressure of dissolved gas against its mole fraction in the solution, is a straight line passing through the origin. It is the shape of the plot. Okay. Now, the slope of this plot gives the value of, that is M. What is M? KH. The slope of the plot gives the Henry's constant. So, the plot of pressure against mole fraction is a straight line passing through the origin whose slope is simply equal to Henry's constant KH. By this method, one can get the value of Henry's constant of given gas or dissolved gas at given temperature or fixed temperature. Next point is, again you consider this expression P is equal to KH into chi, or chi is equal to P by KH. Okay. At a fixed pressure, okay, if KH value for gas is higher, then chi for the gas is lower, because KH is in the denominator. KH in the, or else you can write this one as KH is equal to P by chi. You can write in this form also, that is chi is equal to P by KH. See, higher the KH value, higher the Henry's constant for the given gas, lower will be its solubility. What is chi? Solubility, mole fraction of the dissolved gas. Mole fraction of the dissolved gas means amount of dissolved gas present in the solution. it is nothing but solubility. So, higher the Henry's constant for the given gas at the given temperature, lower will be its solubility in the solution or liquid. Lower the value of KH, higher will be its solubility. See, the gases which have very low Henry's constant, gases which have very low Henry's constant can fairly dissolve in the given solvent, say water, and those which have higher KH values dissolve only at a small extent. You just see, consider the Henry's constant of carbon dioxide is greater than that of helium. Henry's constant of carbon dioxide is higher than helium. Lower than helium. This indicates the solubility of helium in solution is lower than that of carbon dioxide, because Henry's constant of carbon dioxide is lower than helium. Lower the Henry's constant, higher will be the solubility. Or you can say solubility is inversely proportional to Henry's constant. You can say solubility of gas is inversely proportional to Henry's constant. This is about Henry's law on gas solubility, factors which influence on solubility of gases in liquids. Next bit is applications of Henry's law. Actually, 3 applications are mentioned. This one, Henry's law is used in the preparation of carbonated water. Henry's law is observed in the preparation of carbonated soft drinks. Carbonated water, it is nothing but soda or soda water. See, in the preparation of some beverages like Sprite, Coca-Cola, Fanta, etc., etc. Carbon dioxide is passed through the solution or passed through the liquid under high pressure, where large amount of carbon dioxide dissolved in the solution and it is sealed. Okay. So, in the preparation of carbonated beverages, Henry's law is observed where carbon dioxide is passed through the system under high pressure. Then it is made airtight. Next, this Henry's law is useful in explaining some diseases or problems observed by particularly scuba divers, deep sea divers, and high altitude mountaineers. High altitude mountaineers and scuba divers, often they experience a sort of problems. Such thing can be explained by making use of our Henry's law. See, deep sea divers are normally used air for their respiration. They carry air cylinders while studying under deep sea. Air contains nitrogen and oxygen. Purified air mainly contains nitrogen and oxygen. Purified air is a mixture of nitrogen and oxygen can be obtained after removing moisture and carbon dioxide from it. And the deep sea pressure is very high. The deep sea pressure is very high. At high pressure, we know that at high pressure, solubility of gas in liquid is very high. So, at high pressure, more amount of nitrogen and oxygen are dissolved in blood. Okay. Of course, oxygen is used by the body. This nitrogen remains in the blood. When that scuba diver comes to the surface, the pressure is released. When pressure is released, this dissolved nitrogen tend to escape from the body. That is, it tend to escape from the blood. And it will cause, sometimes it blocks the capillaries, which causes severe pain known as bend. Scuba divers often experience this type of disease, that is bend or pain. In order to avoid this one, nowadays scuba divers used a mixture of air and helium. Helium is mixed with air and given to the scuba divers. Okay. In presence of helium, the dissolution of nitrogen in blood is considerably reduced. Okay. As the result, the effect of bend is nullified. Generally, the mixture used by scuba divers consisting of helium, nitrogen and oxygen. Helium, nitrogen and oxygen. Helium is about 11.7%, nitrogen 56.2% and oxygen 32.1%. This mixture, this is the composition of the mixture of air and helium used by scuba divers. This mixture is used in order to nullify or minimize the effect of bend, that is pain. Another one is the high mountaineers. They often experience a sort of problem known as anoxia. Anoxia. Anoxia, it is deficiency of supply of oxygen to the brain, which causes loss of activeness, breathing problem, weakness, etc. See, at high altitude, pressure is very low. At high altitude, pressure is very low, whereas in the deep sea, pressure is very high. On moving above the sea level, pressure gradually decreases. Okay. At higher altitude, pressure is very low. As the result, absorption of oxygen by blood becomes less. So, presence or absorption of oxygen in blood when become less, supply of oxygen to the brain become less. This causes disease anoxia, problem anoxia. That means lack of thinking capacity. That is, thinking capacity decreases, breathing problems develops, weakness develops. These are the things they are experienced. Of course, these problems, anoxia faced by high altitude mountaineers, bend faced by scuba divers, can be best explained by making use of our Henry's law of gas solubility. These are few applications of Henry's law as well as solutions of gas in liquid. Next, we shall see the solutions of liquid in liquid. Liquid in liquid. You know, liquid in liquid solution will be in the liquid state only, in which one liquid acts as solvent, another liquid acts as solute. Let us consider binary liquid mixtures. Binary liquid mixtures or solutions are those which are made up of only two liquids, that is, one solute, another one is solvent. Okay, we shall see those in the next classes.